Alright, so welcome to this second lecture, and in this lecture we will be looking at carrying on where we left off the last one, which is thinking about energy change, and specifically energy change in the forms of work and heat. So if you remember the last time, we sort of boiled it down to this. We said that we would have a chemical reaction and that we would consider that as a system. And we would look at whether that system was exchanging energy with the surroundings, either giving the surroundings energy or taking energy in from the surroundings. And that energy exchange could happen either as work or as heat, where heat is transfer of energy due to a temperature difference, and work is transfer of energy due to expansion or compression of gas. And we said that because of the first law of thermodynamics, the change in internal energy is equal to the amount of heat lost or gained by the system plus the amount of work lost by or gained by the system. So if you remember, we came upon this idea of internal energy because it became quite complicated to think about potential energy and kinetic energy separately. So where does that leave us? Well, that leaves us now with wanting to calculate both work and heat in terms of energy change, because if we want to look at the overall energy change of a reaction, we need to be able to calculate work and we need to be able to calculate heat. So let's look at work first of all. And in chemistry, we tend to focus on work of expansion because that volume expansion due to a gas or volume compression due to a gas expanding or compressing is so much larger than other forms of work. So for example, electrical work is a type of work. So in chemistry, we tend to focus on work of expansion. And if we look at our screaming jelly baby reaction, what we find is we have our sucrose here reacting with oxygen to form carbon dioxide and water. And whether or not we will get work of expansion essentially depends on whether or not the balanced equation shows us whether we have more or less gas molecules as a result of this reaction. So here we see we have 12 gas molecules going to 12 gas molecules. So this equation, as we have written it, actually won't be doing any work. There will not be any expansion of this system because the number of gas molecules are staying the same. Let's have a look, though, in a little bit more detail about how we can analyze this. So in this slide, I'm going to summarize quite a lot of school learning that you've probably come across. Have some tea. And about gas laws. And these gas laws essentially will combine into what we call the ideal gas law. So this will be familiar to many of you, but it's just not in some of the school syllabi. So I just want to check that everybody is up to speed on these gas laws. So the first obviously is Boyle's law. Boyle, an Irishman, born in 1600s and became one of the first members of the Royal Society in 1660. And Boyle essentially did a lot of experimentation around gases and looking at the pressure-volume relationship of gases, and found that if we have a gas, let's say we have a balloon, a gas in a balloon, if we increase the pressure on that gas, then obviously the balloon will shrink. Okay, the pressure and volume are inversely proportional at constant temperature. Charles was a French chemist, again around a similar period, a little bit later than Boyle, and he explored the volume and temperature of a gas. And he found that, for example, if we think again of our balloon and we increase the temperature of that balloon, then if the pressure has to stay the same, well then as we increase the temperature, the volume must expand. So Charles related volume and temperature and found that they're directly proportional. Along comes Avogadro and comes up with the most obvious statement ever, which says that at constant pressure and temperature, as we increase the amount of substance, in other words the number of moles, the volume must increase. So there he goes, he gets a whole law named after him by saying the volume is directly proportional to the amount of substance. And then we finish up with Gay-Lussac law, which says that as we increase the pressure of a substance, as we increase the temperature of a substance, the pressure will naturally increase at constant volume. So if we have our balloon, but now that's fixed volume, it can't expand, and we increase the temperature, well then obviously the gas molecules in that balloon are going to move around much, much faster. so the pressure will increase. And what the ideal gas law does is essentially combines all of these statements into one statement. So we know the pressure is inversely proportional to the volume, we know the volume is proportional to the temperature, and so on. So we combine all of these laws, all of these individual observations, we can create the ideal gas law. And the ideal gas law will use units which are SI units. That means pressure will be in pascals, volume will be in meters cubed, okay, and that's a real pain for chemists because we tend not to use meters cubed. Moles will be in the units moles, and temperature will be in Kelvin. And the gas law, as I've written it here, you'll see it has this pressure, volume, number of moles, and temperature, but we have this additional proportionality constant called the ideal gas constant, or. And or is given the unit, given the value 8.314 joules per Kelvin per mole. All right, and the way we work this out is if you work through these units, okay, we look at meters cubed here, we've got pascals. If you break those units down into core units, well, we'll if you want to work through that, you'll see that we end up with these units, joules per Kelvin per mole. When we say ideal gas law, that comes from the kinetic theory of gases, and the kinetic theory of gases is essentially a very simple model of gases, and says that a gas is a collection of molecules that are moving continuously and randomly. That's a pretty good observation, pretty good approximation. It says that gas molecules will move in straight lines unless they collide, that molecules won't influence each other except in those collisions, and that molecules are infinitesimally small points. So the kinetic theory of gases, which describes an ideal gas, is essentially saying that molecule gases will effectively move around in straight lines around each other and won't deviate unless they collide. So it's a good approximation, but not a great approximation, because of course molecules may come close to each other, and if there's electronic or electrostatic repulsions or attractions, well then obviously those molecules are going to come closer or move further away from each other. So this ideal nature essentially omits any kind of intermolecular interaction. And we can correct for that. So the van der Waals law essentially corrects for these intermolecular interactions so that we correct pressure to take into account attractions between molecules using A, the attraction parameter, and looks at the fact that molecules aren't infinitesimally small points that actually take up a particular volume. So the volume is corrected by V minus an amount to take into account that correction. And we essentially get a more complicated form of the ideal gas law called the van der Waals equation, which is this form here. And you'll pick that up in later years if that's of interest. We don't need to remember it here. All right, so let's have a quick look at this law in action. So we can look at the ideal gas law, PV is equal to nRT, and here we're asked to calculate the mole occupied by the volume occupied by 1 mole of carbon dioxide at that temperature and that pressure. So we can use the ideal gas law. We can say that PV is equal to nRT, and we want to use our parameter. So we're given the pressure in 1 bar. Well, 1 bar is 10 to the power 5 pascals, so we need to use SI units. And we're looking for the volume, so we can rearrange this. Expression. V is equal to N or T over P. So look at the number of moles, 1, multiplied by the gas constant, (8.314), multiplied by the temperature, 300 Kelvin, divided by the pressure. Alright, so my per Kelvin and Kelvin will cancel, my mole and my per mole will cancel, and I'm left with joules divided by pascals. But when we reduce those to SI units, we'll end up with meters cubed, because it'll be in SI units. So that's going to give me a volume of 0.0249 meters cubed, which is equal to 24.9 decimeters cubed. Okay, so I'm going to multiply that by 1,000 to get to from meters cubed to decimeters cubed. Okay, why is that? Because a decimeter is 10 decimeters is a meter. So therefore 1 meter cubed is equal to 10 by 10 by 10 decimeters cubed. So to convert from meters cubed to decimeters cubed, it's a factor of 1,000. So here we have our answer written up. So here are reduced the units, joules and pascals, so you can see how we end up cancelling out and ending up just with units meters cubed. We get meters squared divided by per meter, so we ended up with meters cubed. Alright, so let's have a look more about work of expansion. So what we want to do is take this ideal gas law idea and now use that for calculating work of expansion. And we can say that if we have some solid, so the classic one here is calcium carbonate reacting with HCl to produce a gas, and we want to measure the volume of gas, or the work being done essentially in this reaction. Well, that gas, as it's produced, is going to push up against the atmosphere, and we can essentially measure the change in volume of gas produced, delta V, by measuring how far this piston moves up. So we can very easily calculate delta V experimentally. So the work done will be the work in pushing out that piston against an external pressure, and that external pressure will be, in this case, atmospheric pressure. So we can say that the work is equal to the integral from the initial volume to the final volume against an external pressure. And we say minus here because we're pushing out, work is leaving the system, so it's negative. If pressure is a constant, as it normally is in chemical reactions in the lab, well then this just becomes minus P times the integral of V1 to V2 dV. So this is minus P delta V. So our work done by a chemical reaction due to expansion is minus P delta V. And that means then we can relate this minus P delta V, or this P delta V, to the gas law. So if we have constant pressure and constant temperature, okay, so constant pressure was required to generate this integral in the first place. At constant temperature, we can say the only change that will happen now is the change in the number of moles. So therefore the work being done is minus P delta V, which is minus delta nRT. So this is really useful because now all we have to do when we look at chemical reactions is not work out the volume of expansion in a particular experiment, but we can just look at the chemical reaction and look at the number of gas moles that have changed in the balanced equation. So we can say that if a system expands, well then the number of gas moles that form will be positive. Okay, so if I go back to my calcium carbonate example here the system is expanding because we're going from no gas molecules on this side to a gas molecule on this side. Something gone wrong here in my chemical reaction, but here we have a gas being produced, so delta N is positive. There will be more gas molecules in the products, so energy is leaving the system and work will be negative. So if energy is leaving the system is expanding, we assign a negative value to that work. If energy as work is entering the system, in other words the system is contracting or pushing in on it, well then the system is gaining energy, and the work, we assign a positive value to work. Okay, so let's have a look at our system. Our system was a screaming jelly baby reaction, and we can see here that we've got solid reacting with a gas to form a gas and a liquid, and we want to know what is the work of expansion in this case. So we can have a look at this reaction, but what we find is that, as mentioned, the number of gas molecules don't change. We go from 12 gas molecules in the reactants to 12 gas molecules in the products. So as written, this system is doing no work of expansion. We're going from 12 to 12 gas molecules, so therefore delta N is equal to 0. Because we're only considering gas molecules, the liquid and solid don't make any appreciable contribution to the volume. So therefore, work here is minus delta nRT. so delta N is 0. So we've got minus delta N RT is equal to 0. So at 298 Kelvin, as this equation is written, this system is doing no work. Does that make sense? Well, remember we said that this equation is representing the overall reaction from the start to the very end. In other words, when the reaction has completely finished and all of that water as a liquid, water as a gas that produced during the reaction returned to water as a liquid. Obviously, if we wanted to know the work of expansion done, say for example, before all of the water as a liquid returned to water as a gas, well then we would write this L here as a G, and then suddenly we'd be going from 12 gas molecules to 23 gas molecules, so delta N would be 11. So in that scenario, the system will be doing a large amount of work. It will be 11 times 8.314 times 298. So it is really, really important in thermodynamics to know what the state of the reagents are. So we need to know what exactly it is we are saying. So here we are saying for this complete reaction where water as a liquid is being produced, the system is doing no work. So there's a prompting question here that says chemical explosives often include nitrogen, and asking you, can you think why that is? So I'm just going to give you a minute. You should pause the video and think, well, why would chemical explosives often include nitrogen? What is it about explosives that you want explosives to do? So I'm going to pause for a second and I ask you to too, and I'm going to clean my whiteboard. Okay, so here I've written out the chemical formula for combustion of trinitrotoluene, TNT, a common explosive. And we see here the balanced equation leaves us with 5.25 moles of gas on the reactant side, and 7 plus 1.5 is 8.5 gas moles on the product side. And again, this is assuming that this liquid is in the final state, but in reality, as this is exploding, that liquid is also going to be gas. But let's just look at the overall reaction. So this means that we have 5.25 going to 8.5, so therefore work is equal to minus delta N RT. So it's equal to minus 8.5 minus 5.25 is 3.25 moles times 8.314 times 298. So we'll get some value. I haven't worked it out in joules per mole. We'll get some final value here of the work of expansion. Sorry, the whiteboard is just taking a while to catch up there. So the reason we have nitrogen very often in explosives is A, because it makes slightly more unstable compounds, and B, because it produces this extra highly stable nitrogen gas. So energetically this reaction is very, very stable products. So this drives forward energetically producing a gas. So that means our system, if we imagine our cave or whatever it is where we're going to have our explosive, we pack our explosives in here. As this explodes, it's going to push out in all directions and operate as an explosive. However, we don't often get full combustion. We don't often get the full value of this work. Why is that? Well, as this explosive is pushing out, as it's exploding, it's pushing out this sort of sphere, pushing away all of the air. So very quickly we run out of oxygen. So actually we get incomplete combustion very often with explosives, because the oxygen that's needed to completely combust the explosive tends not to be readily available. Okay, so here are some common explosives. There's TNT that I drew out. Nitroglycerine is another one, RDX and PETN. These are common explosives. And as I mentioned, we don't often get complete combustion because the amount of oxygen that's necessary isn't often readily available. Okay, so that's a consideration of energy loss as work. And as you can see, it's very easy to calculate work of expansion. We just essentially look at the chemical formula and use the delta N, the number of gas molecules that are produced, as a way of estimating what the work of expansion is. What about heat? Okay, so remember our goal here is to work out the change in internal energy. So I've just shown you we can very easily calculate work. What about heat? So again, we need to have a sign convention. So it makes sense to say that if we add heat to a system, the energy of the system will be increasing. We're providing the system with heat, so therefore we ascribe that heat value a positive sign. We are increasing the energy of the system. If we take heat away from a system, the energy of the system will be decreasing, so therefore it'll have a negative sign. And essentially the extent to which we can transfer heat to or from a substance will depend on that material, going right back to Joseph Black's early experiments. So we define the heat capacity as the amount of energy required to raise the temperature of a substance by 1 Kelvin. So how much energy is necessary to raise the temperature by 1 Kelvin? That's giving us a sense of the capacity of the material to take in this energy. And this is distinguishing also between heat, energy, and temperature in Kelvin. And two important heat capacities are the specific heat capacity. This is the amount of energy in joules required to raise 1 gram of substance by 1 Kelvin. So the units are joules per Kelvin per joules per gram per Kelvin. And the molar heat capacity, how much energy is required to raise 1 mole of a substance by 1 Kelvin. So the units are joules per mole per Kelvin. Okay, so here we have these definitions. The heat capacity is specific heat capacity. How much heat is required to heat 1 gram of substance by 1 Kelvin, joules per Kelvin per gram. And the molar heat capacity, how much heat is required to heat 1 mole of substance by 1 Kelvin, joules per Kelvin per mole. And we have to put these brackets around here and say this is a constant pressure, and this goes back to our considerations about the ideal gas law and using the ideal gas law. So these two definitions are very useful because this tells us straight away if we have a gram of substance or a mole of substance, we get a sense of what is the heat capacity. So we can very easily work through this. So here we have an example of 100 grams of copper. We know it's the amount of heat we're providing, so I don't think I even need to work that out. We can just easily say delta T here, if we rearrange the equation, will be the amount of energy we're providing divided by the mass of the substance times the specific heat capacity. So I've just rearranged the equation on the previous slide. And if you put in the units, joules here, grams here, joules per mole joules per gram per Kelvin, that will give me units Kelvin here. Alright, so it's very easy to use that calorimetry formula. And this is the basis of the lab experiment, which I think you've already done. So this video will go through that experiment in detail, but essentially this is looking at using those calorimetry values, that idea of calorimetry and heat transfer to work out heats of reaction. And this experiment, I'm not going to go through it in detail here, but you've done it in the lab. We can essentially work out first of all, calibrating the calorimeter. So the calorimeter itself will lose heat, so we need to first of all work that out, and then doing the experiment whereby we will work out the heat transfer by measuring the temperature increase. All right, so you should have a look over that lab experiment if you haven't already done so. So what we've been saying is we can very easily work out the work, heat expansion or contraction. We can very easily work out the heat gain or loss. So therefore we can very easily work out the change in internal energy. And we mentioned that we ascribe signs to these. Work and heat are negative if energy is leaving the system. Work and heat are positive if energy is entering the system. So this means now that we have another slightly more nuanced way of writing our reaction profile diagram. Now on the y-axis, as I mentioned, we can put internal energy U, and the change in internal energy here between reactants and products is very easily calculated by measuring the work lost or gained and the heat lost or gained by the system. But this is a bit of a pain. Alright, we don't want to be constantly going around and looking at the amount of heat lost or gained by the system and the amount of work lost or gained by the system, because it just takes far too long. So chemists, because we often deal with chemical reactions and use chemical reactions where there is work of expansion as well as heat of expansion or heat of reaction, we tend to use, instead of heat or work or internal energy, we instead use the idea of enthalpy. And enthalpy is defined as H, is given the symbol H, and that's defined as the internal energy of a system plus the pressure volume expansion. So enthalpy implicitly considers the pressure volume expansion. So now we don't have to look at chemical reactions and go, what is the heat loss or gain? What is the work loss or gain? Therefore I have my internal energy. Enthalpy includes in it that pressure volume expansion. So we don't need to consider that separately. And that's really, really useful in chemistry. And the reason it's useful in chemistry is because if we look at our definition of enthalpy, so I've said that enthalpy is equal to H is equal to U plus PV. Well, we're not interested in enthalpy itself, really. We're interested in change in enthalpy. So that means it's going to be delta H is equal to delta U, my pen has just changed there for some reason, plus a constant pressure P delta V. Alright, so we've got now our changes. So delta H, well, delta U we know is Q plus W, and P delta V, well, we said that work is equal to minus P delta V, so therefore P delta V is equal to minus W. So that means that delta H, sorry, the pen color keeps changing, delta H is equal to Q plus W minus W, so delta H is equal to Q. And we had just put again a subscript P here to indicate that this was under the condition of constant pressure that we labelled here. So that means now we can relate the change in enthalpy, which implicitly includes this pressure volume work, directly to the heat lost or gained at constant pressure. And this is so useful to chemists because we've seen it is so easy to measure from using calorimetry the heat lost or gained. So therefore we can directly relate this enthalpy value to the heat loss or gain at constant pressure. So that means, and I'm not going to go through this in detail, but you can try this question. That means when we do some calorimetry experiment and we work out the heat lost or gained at constant pressure, well then we can directly relate that to the enthalpy change. Okay, and so much chemistry is carried out at constant pressure that we can very quickly relate calorimetry data to heat loss or gain. And in the next lecture we'll look a little bit more at calorimetry. Alright, so where are we? So where we started off really talking about the y-axis here is energy. Now we've moved it on to internal energy, and now further still we can move it on to enthalpy. And this is the reason we're doing this is just to make the discussion of chemical thermodynamics much easier to relate to experimental data, much easier to conceive. So now with this enthalpy on our y-axis, we can look at chemical reactions and describe them as being exothermic if they give off heat, as this case does, or endothermic where the energy of product is higher than the energy of reactants, so the system is taking in heat. So we describe chemical reactions as being exothermic or endothermic depending on whether it has a negative delta H, in other words the system is losing enthalpy, or a positive delta H, in other words the system is gaining enthalpy. So our task the next time will be to look at clever ways of measuring calorimetry and relating that to the enthalpy. One thing we need to check though is, well, the discussion so far was at constant volume, but also, constant pressure, but we can also have constant volume. So let's say we do the same kind of analysis where we say delta U is equal to Q plus W, but now we're at constant volume. So we have constant pressure, constant volume, so that means we have the heat at constant volume will be equal to the change in internal energy. All right, so the heat at constant pressure was equal to the change in enthalpy. The heat at constant volume, when delta V is equal to 0, well, delta U will just be equal to Q. So that means if we do experiments where we measure the heat change at constant volume, we're measuring the internal energy. If we measure the heat change at constant pressure, that'll be the change in enthalpy. And as chemists, we tend to be constant pressure, so that's why chemists tend to use enthalpy change much more. But there is an experiment where we do use constant volume. So I'm just going to share the whiteboard again. I'm just going to talk through this experiment a little bit more. Okay, so we have here what's called a bomb calorimeter. And the bomb calorimeter is essentially a flask, okay, where the walls are adiabatic. So this is a flask that's pretty good at keeping in heat. And we have a lot of water in here. And in this we immerse our bomb. And our bomb is going to be a sealed metal container. And we'll have our sample. So our sample might be some kind of pellet or something, some solid we want to measure the enthalpy of combustion of. And we will wrap a metal coil around that and bring that out and connect it to some electrical source. We seal up this metal container and then pump in a very high pressure of oxygen. Okay, so maybe I can't remember what the value is. I think it's something like 5 atmospheres, but a very, very high pressure of oxygen. And what this does then is it creates essentially a highly explosive environment in this bomb. So then we step back, we press the ignition source, and this sample will explode. Okay, so if this is an organic substance, it will react with the oxygen in the chamber and it will combust completely. And as it combusts, the heat will leave that bomb and pass into the water around. And as it does so, it will increase the temperature of the water by an amount, delta T. So we're able to work out what the change in temperature is for this particular amount of substance. So we'll know the mass of that substance very accurately. So this technique is called bomb calorimetry, and it essentially is a very good way of determining enthalpy of combustion. So as I mentioned, we have our sample, usually in a pellet, and put into this chamber with high pressure oxygen injected. We ignite it and then we measure the temperature change in the surroundings. And because this temperature change relates to how much energy was passed into the water, if we previously calibrated this, so we can use a what we call the calorimeter constant, and this is where a sample where we know how much energy will be passed to the surroundings to heat up the water by. So we can work out a situation where we know QV, we know what the answer will be, we measure delta T, so that'll give us a calorimeter constant. So we always have to calibrate it first, and then we go back and do the experiment a second time with our unknown. So now we know C cal, we know delta T for our unknown, so we can work out the heat given off a constant volume, which will be the change in internal energy. This is a really easy way of measuring things like the number of calories in food, or the number of the energy in fuels, or whatever. Very easy way of working out enthalpy of combustion. Alright, so let's have a look at an example of that. So I'll just go through this pretty quickly. So here we have a sample of sugar. This is a different type of sugar, D-ribose, and we know the mass of it. And a previous experiment has given us the calorimeter constant. So if we know the mass, well, we can work out the number of moles, so we can find out that we know the internal energy will be the calorimeter constant times delta T. So the calorimeter constant is that multiplied by the change in temperature. So we know that this many joules was given off for that many moles, millimoles. Okay, so I've worked out the 0.727 grams is this many moles. So therefore we can work out, well, how much energy is given off per mole. So I just divide 10,192 divided by 4.85 by 10 to the minus 3. So So that gives me the energy loss, the energy of the internal energy change as a result of combustion. But I also want to calculate delta H. Well, delta H is delta U plus P delta V, which is delta U plus delta nRT using the ideal gas law. So I can plug in my value for delta U, 2.1 by 10 to the power of 6, multiplied by the change in system due to pressure volume work. And here we see, if we look at the balanced equation, we'll be able to see that there is no change in gas molecules. We saw that with sucrose. So therefore the internal energy change and the enthalpy change are the same, because this system is not doing pressure volume work. So they're the same. So we can very easily relate enthalpy and internal energy using the definition of enthalpy. All right, so there's just the equation there to show that we're going from 5 gas moles to 5 gas moles. So again, as this equation is written with the state of water being a liquid, this system is not doing work of expansion. Okay, so I want to leave it there. The next time we're going to continue on with enthalpies, because this is really the focus of the first part of this course. This is the really useful output of this part of the course. And we'll be talking more about this idea of exothermic and endothermic reactions. So I will see you then.